When you do horizontal shrinking, you must realize that it has to do with the 3, or the coefficient of theta, which is in this case 3. So, but before we can do the stretching or the shrinking, I must first have 3 times something. So I must write this sine 3 theta plus 180 degrees as sine 3 times something, and the something will now be theta plus 60 degrees. So then I have a factor of 3, and that happens to be that the graph will now go 3 times faster through a period. We will start by drawing the graph of sine theta. This is now the green graph that you see here. It is just stretched out because we have more values here, and it's also drawn on a bigger interval as that's stated on top. No, it's still from 180 to 360. It's just stretched the whole graph to include everything. So what's happening now? Then we do the stretching. So it is 3 times that. That means the shrinking, because it runs faster, is 3 times faster. So in one period, and the period goes from C to G, the graph has 1, another 1, and another 1 in that same time. Sine of 3 theta. If I do that first, and here's another one. If I do that first, then I have the shrinking part. Now I have to do the shifting part. So that means that each and every value here, because it's plus 60, I have to move it to the left. So that point must now go 60 degrees to the left. And I've shown it here with the orange graph. So if I look at plus 30 here and I move 60 to the left, then I get K value. And if I have D there, this value here, 150, move it 60 degrees to the left, then I get the value at D, etc. So everything that we did with the vertical shrinking, just the whole graph just shifts 60 degrees to the left. Let us now just write down what we said on the previous page. First of all, we must write sine of 3 theta plus 180 as 3 times something. So this is actually my angle. So I will do it in 2 steps. I will start with the shrinking, and then so this is my shrinking, and this is my shifting. So the period in this case is 360 degrees divided by 3, which is 120 degrees. My amplitude stays exactly the same, and the roots, as you can see, there are now many roots. So in one period of sine, we have now C, M, N, E, Q, R, G. So the roots where we had previously theta, so the roots are here. Let us just write some of them down. So it's at I, J, C, M, dot, dot, dot. In general, the formula will be, for the regular function, is theta equal to, remember I set up I like the 0 degrees there, so let me just leave space for the 0 degrees, plus k times, the roots was k times 180 degrees. But now we're dividing by 3, so the new roots will be divided by 3, and we will start in this case again at 0 because there is a value at 0, because the shifting happened it coincide with the shrinking because 180 divided by 3 is 60 degrees, so, and the shifting was also 60 degrees, so in this case we can leave the theta there, or we can the 0 there, or we can leave it out altogether. So the general formula is then just k times 60 degrees, where k is an element of z. We can quickly check it. If k is 0, we get 0. If k is 1, we get 60, 120, 180, 240, all the multiples of 60 degree, and also for the negative values. The extremes, they are again y equal to minus 1 and y equal to plus 1. And again, instead of extreme values at just if we start with any extreme value, if we look at the minimum here, let us take L. If we start at theta equal to 30 degrees, then to get to the next one there, I have to add 180 degrees, which is 3 times the, is it correct, 30, 60, 90, up to 150 is just 120 degrees. So it should coincide with this value here, because here we have 120, so it should be the same as that, 120 degrees, k element of z. And for the maxima we will have minus 30 plus k times 120 degrees. Normally with the extremes we have the full period, like here the 120, and with the roots we have half of that, half of the period. So these are the values that we need, and it's a good exercise every time to look at all that general solutions. The next page is just a summary of what we said on the previous pages, and again it's a good exercise to work through it and make sure that you understand how this 3 and that 3 connects, and how it connects with the period, and how it connects with the minima and maxima. And then I always do my basic function, even if I do it in a broken line, my basic function, the basic sine function, and then I do the shift, the shrinking, and then I do the shifting, and or you work from left to right, but it must be in that form before you can do shrinking and shifting, because it's not shifted 180, it's just shifted 60 degrees, and that will be to the left, because we plus 60. It's the reverse from when you do vertical shifting. Then if you say sine plus 1, we shift up, plus 1 is up, and if we say sine theta minus 1, we shift down. But with the horizontal shrinking, it is the opposite direction, and we saw it with the table. As a bonus, I've help you to solve this equation here, a sine of 3 theta plus 180 degrees. So what I normally do is I put that 3 theta plus 180 degree, I put that equal to x, and then I'm back at my original sign, my mother function sine x equal to 0, which I know the answers of. So once I have the solutions for my sine x equal to 0, then I plug back the 3 theta plus 180 degrees, and then I solve for theta, and then I get exactly what I had before. But now you will recognize here we have a minus 60 plus k times that. But we can just as well write it as a new k, because that 60 there, I can factorize it, then I get k minus 1 times 60 degrees. So you can just write it as a new k. It's just, it doesn't matter where you start, it's just you want to go through all the numbers. So this is how we normally will solve such an equation. So it's exactly the same as we did on the previous page, and this is, you will do a lot of this in first year mathematics, but then you will work in radians. So, but the principle is exactly the same.